things.
Happy Thursday. And the last Thursday of February. I think we're only 2 weeks away from spring break already. Hard to believe. We didn't quite finish up the problems with motion in space. We're going to finish that up today. Take a quiz on motion, discuss the first test, and then move on to multivariate functions. Bless you.
Thank you.
Bless you. Point P moves on the circle given by r cosine beta, r sine beta, with a constant speed of v. Right, so v is the linear speed. Show that if the radius vector to P moves with an angular velocity of omega and angular acceleration alpha, then the linear speed is r times omega, and the linear acceleration is r times the square root of omega to the fourth plus alpha squared. Is it supposed to be squared, or is it supposed to be to the fourth? Supposed to be squared. The first thing we want is our velocity vector, right? Which is dr dt. So what would the derivative of the first component be?
Negative r sine of b times b.
Y times beta. Right, so why is it times beta? You're right to use the chain rule. It'd be the derivative of beta with respect to time, right? That's what the chain rule says. Take the derivative of what's inside. So it'd be negative r, and I'm going to use the dot notation because I don't feel like writing d beta dt. Second component. Bless you. Is that 3 different people now who sneezed, or is it one person sneezed twice? Fair warning, if I now get sick again, you fail. And you're already screwed because I'm already getting a sinus infection, so I'm already there.
Times the derivative of beta cosine beta.
Well, what is the derivative of beta? Derivative of the angle is the angular velocity. So there is our velocity vector, which makes our linear speed right, the magnitude of the velocity vector and it shouldn't be too difficult to see. We have an R omega common, so factor it out. Actually, it's not specified in there. We're going to make the assumption that P is moving in the positive direction. So counterclockwise. Otherwise, that would be absolute value of omega. Right? R is obviously always positive, but omega could be positive or negative, depending on the direction we're going. What?
You don't see omega. What are you referring to? When you say omega? It's just a dumb question.
That's the Greek letter omega. Lowercase omega.
Gotcha.
Right? Uppercase, if I remember correctly, is
Yeah, that's what I was looking.
yeah, that's uppercase omega. Right, so that takes care of the linear speed portion. Linear acceleration. Oh, I'm just going to need the acceleration vector first, right? Right, dv dt. First component. Is that it? Well, that's where the omega square comes from. What's omega? What does it represent physically? Isn't that a function of time? So beta is a function of time, and so is omega. What rules should we be using? So there's another piece to this derivative.
That there, we can still take it out as a constant. Well,
Well, remember, I'm not really taking out as a constant. It's being taken out as a scalar function. Right, so that still works the same way. Where'd you get the cosine squared from? You're really overcomplicating this. What does the product rule say? Right, so if you take the derivative of f times g, what is that derivative? Right? Isn't that derivative of g times f? I took the derivative of the second function multiplied by the first. So plus, we have to take the derivative of the first function multiplied by the second. Derivative of r omega. Isn't that just r omega dot? Right, because r is a constant. And the second function was sine of beta. Right? Now, we know that r is constant because we're told this is a circle. If it was not a circle, r would also be a function of time. Right? Because it'd be a function of position. In which case, this derivative would have been a product rule, right? Velocity had been a product rule, and then acceleration would be a double product rule, which is always fun. Second component. See that, wouldn't it? We already know what beta dot is, right? That's omega. What's omega dot? So what's the derivative of angular velocity with respect to time? So it'd be alpha, right? I forgot. Turn you off. That's a terrible looking alpha. Better. That would be acceleration vector. Oh, bummer. All we can factor out is an R. Linear acceleration. We can factor out the R. Now I have to take the magnitude of what's left. Oh, wait, why am I doing R squared? I already factored out the R. Right, this is the first term square. Oh, no, I'm sorry. No, that's not right. I'm missing my middle terms. I did the student square, not the actual square. So there needs to be a plus 2 omega squared alpha cosine beta sine beta. There's the first term squared. Second term. A minus 2 omega squared alpha sine beta cosine beta. Right, and as before, that notation is going to mean that's the square root of that entire thing. We're right off the bat. The middle terms can't hold. You have two terms with an omega to the fourth. Factor that omega to the fourth out of those two terms. Gonna be left with cosine squared plus sine squared. Do the same thing with the alpha squared. Factor the alpha squared out of the two terms that it's a common factor to, right? Left with a sine squared plus cosine squared. And of course, each of those sums is 1, and we get the desired result.
First term go.
Well, first term.
The radical. Sorry.
Here?
Yeah.
It's right here. Right, what I did with this is I just factored out the omega to the fourth from the two terms that it's common to. Right, so this one and this one. Right, so I just grouped those two together first. Then I did the two terms that have the alpha squared. Right. And that's because addition is both commutative and associative. Basically meaning the order in which you write addition does not matter. Right, so that proves the linear speed and linear acceleration. By the way, contrary to popular belief, a lot of what we did in this was not really plug and chug, right? It was a lot of deriving stuff. That's what physics is. Your introductory courses, you already have the formulas for you. And the upper courses, you get to derive all those formulas. You don't get to take anything for granted. So it's more along the lines of what we just did here, not like, oh, you have a particle moving with a velocity of blah. Just you have some arbitrarily charged sphere, calculate the electric force on it. Have fun. And that's basically what it is. That's also what upper level math is too. It's not a lot of the calculations, it's more of the proofs. But of course, again, we made some simplifications here, right? Probably meant to put it in there, just didn't, that it's moving counterclockwise. That's what allows us to assume that omega is positive. So we can just get rid of this absolute value. We also ignored quantum mechanical effects. I mean, it is a particle. So, I mean, technically we should be considering quantum mechanical effects on it, but we ignored that. We just assumed that it's a point mass and not an actual particle. But even then we ignored thermodynamical effects, statistical effects. Yeah, so we made a lot of simplifications in these problems. We also ignored friction. Projectile motion made one very convenient simplification, and that is that there was no air resistance. If there is air resistance, then that model is no longer valid. Right, that model assumed there was only one force acting on the projectile, and that was the force of gravity. And that's simply because if you now put friction into it, the problem becomes even in my mechanics class, level 300, the only friction we looked at was air resistance of skydivers. We didn't even consider rolling friction or kinetic friction, static friction, because it just made the problems way more hideous. Questions on anything we did with vectors? So disappointed all of you haven't turned in the test yet. It was due the 21st. So sad. Oh, I didn't even create a Any day now. First test is now available. It'll be due before the start of next Thursday's meeting. Right. Need to show all of your work to receive full credit. Test needs to be uploaded as a single PDF file, minus if I ask you to plot some on Mathematica, any screenshots can be a separate file. Right, but your work itself needs to be a single file. Right, so you'll do all of the work on loose leaf paper. When you're finished, use any kind of scan app you want to scan it as a multiple paged PDF and then upload it. Allowed to use your notes, textbook, any official course material. So that's also the 3 tables that are posted on Teams, right? The pre-calc review, the table of derivatives, and the table of integrals. You're also allowed to just use Mathematica to evaluate integrals if you want. That's fine. I don't care. You can have it evaluate derivatives for you too. I don't care. Right, I'm more concerned with the setup and can you interpret the results. You may not discuss this with anyone except me. Well, you can't Google the answers. Trust me, I'm probably gonna know if you got the answer online. Because it's probably gonna be worded way differently than I would expect a student to word it. Will be due 2nd of March. That is before next Thursday's class. At the top of the page, obviously, you're going to want to put your name on it. Actually, you don't really need to worry about a name, do you? Because it's going to be uploaded, so you're fine with the name. Top of the document, you're going to want to write out the statement, basically saying that, yeah, I'm not cheating. Most importantly, have fun. Five questions. I feel like it's fairly simple. This test was kind of a bore for me to do, but it's vectors, and vectors are boring by nature. I've already written the second test. That was a little bit more fun. Looking forward to the third. Any questions? And let's do this while I get set up for the next topic. We'll do what, 15 minutes, and then we'll continue on. Yeah, bring me any things to this. Sorry. Calculus 1, also referred to as differential calculus, right? Because for the most part, what you study in Calc 1 is the derivative. Calc 2 is referred to as integral calculus. Again, because for the most part, what you're studying is the integral. Calculus 3 is known as multivariate calculus. It's the study of multivariate functions. Right? All of the functions that you have studied up to this point have been what's known as single variate. Right? F of x, v of t, a equals pi r squared. Right? Even the area functions, right? Length times width, you can write as single variate, either as a function strictly of length or width. It is very, very rare to have only one variable, though. Right? There's usually a lot of variables. So area technically is what's known as a two-variate function for rectangles, right? It's a function of length and width. And a circle obviously is still just single variate, pi r squared. Triangle is a function of base and height. 1/2 base times height. Even temperature, right? If you're on a hot plate, it's a two-variate function. Depends on your x and y coordinate. Right? If you study physics, you're dealing with 4 variables. Time, and then your position in space, x, y, z. Unless you're studying string theory, then it is 10 variate. Time and the 9 spatial coordinates. That's a discussion for a different class. For the most part, why are you up there? That's not where I wanted you. For the most part, we restrict our study to 2 and 3 variate in this course. We will look at some more variates, but for the most part, it's going to stick to 2 and 3. Now, when you had a function, y equals f of x, right? Had a domain, and the domain was an interval, wasn't it? It was an interval for x. You had an independent variable, which was typically your horizontal axis, right? And then you had the dependent variable, y, which is your vertical axis. So a function y equals f of x always gave you a 2-dimensional curve. Two-variate function, z equals f of xy. Well, now your domain has to be a set of ordered pairs that can be plugged into the function, right? So set of xy. Well, that's now a 2-dimensional domain. It's known as a region. You have the 2 independent variables, x, y. You have 1 dependent variable, z. So every function, z equals f of xy, gives you a 3-dimensional object, a surface in space, if you will. Three-variant, w equals f of xy, z. Now your domain is a set of ordered triples that can be plugged in, right? So now our domain is a region in space, right? So typically referred to as a solid. And the function itself gives us an object in 4 dimensions, if you will, a hypersurface, a hypersolid in hyperspace. Then obviously 4 var would be 5 dimensions, 6 would be 7 dimensions, so on and so forth. So with each increase in the number of variables of function, both your domain increases in dimensions and the resulting graph, for lack of a better term, increases in the number of spatial dimensions. Even as simple as 3 variate is impossible for us to plot, because we cannot plot 4 dimensions. It's hard enough plotting 3 dimensions on a 2-dimensional paper. Plotting 4 dimensions is just downright impossible because we cannot even conceive of the 4th dimension. It'd be like a 2-dimensional being trying to comprehend the 3rd dimension. To us, it's simple because we live in 3 dimensions. And now for us trying to conceive of the 4th spatial dimension, it's just impossible. A good way of viewing it, though, deals with shadows. Right, so we can think of a 4-dimensional object in terms of the shadows it makes on 3-dimensional space. Right, much like if you're trying to plot a 3-dimensional object, you typically think of it in terms of its projection on the XY plane. Right, you can think of those as the shadows on 2 space. So a 4-dimensional object has a 3-dimensional shadow. So it could have a sphere. And it's really weird. If a higher dimensional object were to interact with our 3 dimensions, best way again is to think of this cup. So think of a 2-dimensional being living on your table or whatever. Right now, the 2-dimensional being would see nothing here, right? Set it down, what does he see? Just sees a circle just popped into existence out of nowhere. Now imagine this is now moving through their plane, right? Pops into existence, the circle will start to change shape as it moves. And then once it's out of their world, it will just disappear as quickly as it appeared. And it would be unexplained to them. So even if you don't believe in aliens, is the idea of UFOs now so absurd if you consider higher dimensions? Could just be a 4-dimensional object interacting in our 3-dimensional world for that brief period of time. It would seem to disobey all the laws of physics because we're only thinking about it in terms of 3 dimensions, not 4. In 4 dimensions, maybe it's obeying every law of physics. So a lot of the quote-unquote unexplainable can now be explained if you think of higher dimensions. Really good novel on this is Flatland. Complete fiction, but it does a really good job of explaining it. And there is a sequel, I think it's called, what, Flat World? That now takes it from 2 dimensions to now a 3-dimensional world. Invitation. And again, keep in mind, I was talking strictly about 4 dimensions, but string theory says they're 9 spatial. So now it gets even more absurd. Oh, fun times. This is why I'm not going for a physics PhD. Functionally, multivariate functions behave the same way. All of the laws of functions you studied in pre-calculus still apply. How you add them, how you subtract them, multiply, divide. There is one thing that you lose, though. We've now lost composition. Right? How would you composite a multivariate function with a function? Because there's more than one variable. Right. Now, if you have multiple functions, right? So you could composite a two-variate function with two different functions, right? Have one function represent x, one function represent y, and then you could get into a single variate. And we do consider that with partial derivatives with the chain rules, right? If you have a function of x, y, z, let's say, you can write x, y, and z as functions of t, when I can write f as now a single function of t. That means evaluation of multivariate functions are the same. We're given f of x, y equals x plus y times x to the fourth, and we're asked to evaluate this function at 3 points, -1, 3, -4, 2, and -1, -3. Order matters, right? For f of -1, 3, since it's a function of x, y, replace x with -1, replace y with 3. And that's f of -1, 3. Right, so we have -1 plus 3, which is just 2. So what is -4 to the fourth power? 256 times 2, 512, minus 4, it's 508. F of -1, -3. -4, right? And obviously this just naturally extends if you're dealing with 4 variate, 8 variate. It's all evaluated the same way. Right? Well, remember when we were talking about functions, defining it in Mathematica, or if you're storing a function in your calculator? Right? F is your function variable, is the function variable, what you're calling the function. We're calling it F. Then it's of x, so that underline is specifically telling us we're defining this as a function of x, so x can change. And then you go, colon equal says its definition, and then you just type in whatever your function is. Same thing with multivariate. Now we have 2 variables, so I'm going to say it's function now of x and y. Both are underlined. Now here's where you have to be careful. Notice that y and x are both blue when they should be green. You cannot do implied multiplication. It is reading yx as a single variable. not two variables. So it's actually reading this as the variable yx all raised to the fourth power instead of y times x to the fourth. Shift enter, it's now stored, and now we can just go ahead and evaluate, right? -1, 3. -4, 2. -1, -3. So 2, 5, or 8, -4. So that's how you would define multivariate functions in your calculator or Mathematica. When looking at a two-dimensional, or I'm sorry, three-dimensional object, you're trying to plot 3 dimensions, there are several ways that we can look at it. So you can look at its traces. Right, so what will it look like if we only consider the xy plane? What will it look like if we only consider the yz plane, right? What does it look like if we consider the zx plane? Right, so those are the traces. We also have level curves. Right? Level curves is essentially a shadow on the xy plane. Every three-dimensional object has an infinite number of level curves. A single level curve is of the form c equals f of xy for some c in the range. Right, so I could say, what is the 2-level curve? Then that would be f of xy equals 2. And then what is that shape? We're just going to go ahead and use Mathematica to plot contour maps. Collection of all the level curves is called a contour map. Topographical map, a topographical map that shows elevation with lines, that's a contour map. But if you look at weather maps, the isotherms, those are contours. Those are contour maps. Right, so it is used a lot. Going to use the contour plot. Right, but here we're not using it to plot a relation, which is what I have been using it for. Now we just type in the function. First one was y minus 2x squared. We still need to put in a range for each variable. I just went minus 10 to 10. This is technically all you need. And this will be the result. Right, which to me isn't really useful. That's just some options. I don't like it being framed, so I'm going to turn the frames off. Doing so without making any other adjustments. Okay, that's nice. Now let me turn axes on. Perfect. It looks like it's already set to have the origin at the actual origin. So I don't need to worry about adjusting that. Now what you can do, right, is if you scroll. So that is a level curve that corresponds to C being negative 175. This one would be C equals 0. Right, that'd be negative 25. Notice there's no positive C's in here. Right, that means that C can't be positive. Although I'm sure there would be some positives in here if I actually forced it to plot. Because I'm pretty sure you don't only get negative numbers out of here. In fact, I know you don't. If x is 0 and y is any positive number, it's positive. So you can get all the real numbers out of this. You can adjust the actual C values themselves. Forget the command for that. Documentation. Contour plot. Options. Which one is it? I think it's contours. No. Yeah, it is. It's contours. Because let's say I specified I wanted certain levels. Right. Say I said I wanted 1, 2, 3, 4, and 5. I'm gonna have to do this. No, I didn't like that. Right. 1, 2, 3, 4, 5. Unless it specifies for contours, you can just let Mathematica do the contours automatically, which is its default. What I am going to include, though, plot legends. So what that will do is kind of tell you what the colors represent in terms of the contour level. And then you could have some fun with this. You can actually change the shading using some of the gradients that are built in. That'd be this one here. Okay, it'd be the color function is what I want. Maybe. Yeah, I definitely want the color function. And that's not the only gradient that they have. I mean, they have quite a bit. I think one of them is watermelon colors. Yeah, there it is. That's when you can really have some fun with this. I know they have neon colors. Like I said, you can have some real fun with this setting the color function. The default colors, in my opinion, meh. I actually really like the watermelon in this case, so I think I'm gonna stick with that. I think that actually works out really well for this one. And then the problem, can I actually do that? If I do that, and no, it won't let me. I think what I'm gonna have to do is do the screen cropping or screen capture, whatever it's called. All right, so that'd be the contour map for the first function. I'm actually going to use the same thing. The next function was what it was, x squared plus 3y squared. Change this to sandy terrain. Why not? Right, so these are ellipses, right? Again, what you can do is kind of think of this as like its shadow on the xy plane. Right, so if you're to plot the actual function, you can kind of think of this as its shadow. These are hyperbolas. Now I'll let you look at the last one yourself. Something's kind of boring. See if I can actually find mathematic that color. Nope, that's a package. That's not what I want. Yes, excellent. There it is. Color schemes. Because that's a list of all the color gradients that Mathematica has built in. If you're interested in looking up that list. I actually had it saved, but then got a new computer and reformatted it without converting the document, and I'm just too lazy to reprint it. So just look up Mathematica color schemes and you have a full list. So you can really have some fun with it. All right, tomorrow we'll finish this up. If I have to, I will take the whole period instead of a shortened 15 minutes. I have to get through multivariate functions. Because we're also going to look at, within this section, taking limits of multivariate functions, which not as easy as it was in Calc 1. Limits in Calc 3 are actually quite difficult, as we'll see. I will see you all again tomorrow morning.